Good afternoon, everyone. My name is Madhav Sanjay Patil. Before starting my presentation, I would like to ask a seemingly simple question. What is time? I don't want philosophical answer, first of all. At least
It's
try.
a dimension just like the three dimensions like
Yeah, you can
The time
say
is the fourth
that it is a
dimension.
dimension, but it's a hypothetical dimension which cannot be perceived by human mind. So, what scientists or physicists define it as, time is a quality of reality that allows us for a change, and we perceive the time elapsed by noticing the differences in the things around us. Time has not always been existent. According to the special theory of relativity given by Einstein in 1905, at the time of Big Bang, that is about 13.7 billion years ago, space and time did not exist, and all the matter of universe was concentrated in a tiny ball. We all know that time is measured by motion in space. So without motion in cosmos, the time was inexistent. What if I say the time around us can be changed or can be affected by something as simple as how fast you are moving? So in this presentation, I am going to give you a small or brief introduction to the concept of time dilation. So let us begin by understanding what actually time dilation is. Time dilation refers to the different rates at which time passes for different observers moving relative to one another. This means that time passes fastly or slowly for one observer as compared to other, depending upon the magnitude of their relative speeds. Well, does that make even any sense? Actually, it all says that according to the theory of relativity given by Albert Einstein, different vehicles or different objects moving different velocities will have a relative speed between them. Hence, they will have inertial frame in special theory of relativity. So we'll see that how special theory of relativity links to the time dilation. The formula that I gave you now is actually a formula given by Einstein referring to the different times and time dilation. This is the time for an observer in different frame, and this is also a time for an observer in different frames. Here V refers to the relative velocity or velocity comparable to the speed of light. So when I am talking about time dilation, I want to say that according to special theory of relativity, we think that time is not relative because since childhood, we have been taught that time is absolute or fixed in every corner of universe. However, Albert Einstein said that this is wrong. Time is not absolute. According to the theory of relativity, time depends on how fast you are moving. If you are moving very fast, then this velocity will also be affected. And if the velocity is affected, the time in different frames will also be affected. According to the theory of relativity, time and space are not different entities. They are interwoven together to form a space-time continuum. So, and the presence of mass and energy affects both of them. That is why when you move at very high speeds comparable to the speed of light, you can see the changes in time and space. That is, the changes in time and space become quite noticeable. Also, to illustrate this, let us think of one program in which you are astronaut and you are in a spaceship traveling across the universe at a speed comparable to the speed of light. So if you are traveling at a speed comparable to the speed of light, according to your own perspective, the time is normally flowing for you. However, for someone who is observing you from the earth, the time has slowed down for you. The time has slowed down for you means that the time is dilated for you as compared to the reference or in the frame of reference of a person observing you from the earth. Now you might also think that, is motion the sole reason behind time dilation? Is my speed only the cause for time dilation? No, not actually. Even the gravitation can also affect the passage or flow of time. That is, gravitational force has a tendency to affect or distort the space-time continuum, and by distorting it, it hence affects the flow of time. It has been mathematically and experimentally proven that in the presence of strong gravitational field or at high gravitational potentials, the time tends to slow down. Time tends to slow down? What does that mean? It means that if someone is hovering near a black hole, the most dense objects in our universe, then the time would pass very slowly for him as compared to a person far away from the black hole. Now you all must be thinking, then why does this even matter to us? Because as of now, all of us know that we are not able to reach the speed of light or travel at the speed of light, or will not be able to humanly reach black hole, because the nearest black hole is also about a millions of light years away from us. But let me tell you that it has been experimentally observed and calculated through various experiments that time dilation actually exists, and the most famous example to demonstrate this is the muon experiment. What does the muon experiment say? The muon experiment is a classical experiment and demonstration to and a proof for muon experiment and a proof for time dilation. In this, the main element to study is the muon particle. Muon particles are subatomic particles that are formed due to cosmic rays when they enter the atmosphere of Earth. These muon particles have an average life of 2.2 microseconds and are formed generally at a height 10 kilometers above the surface of the Earth. So for just a second, you assume that they travel at a speed of light, and we know the speed of light is 3 into 10 raised to the power 8 meters per second. So if they are traveling at the speed of light, will they be able to reach the surface of the Earth? So let's use some maths. Their average lifespan is 2.2 microseconds. So 2.2 microseconds into 3 into the 10 raised to the power 8 meters per second will give us the distance they will cover. So 3.3 into 10 raised to the power 8 into 2.2 into 10 raised to the power minus 6 gives us 660 meters, which is very less as compared to 10 kilometers height. So our logic says that they won't be able to make it up to the photonic detectors present on the surface of the Earth to get detected. But here is the catch. They do reach the surface of the Earth and are detected by the photonic detectors in actual. So how does this happen? The science today is able to explain this using only one phenomenon or one thing or a theory, that is time dilation. So whatever theory I told you till now, we'll be using it to explain this effect of muons reaching the Earth. So for this, we'll take two observers. First, observer standing on the Earth observing the muon that has just entered the atmosphere at a height of about 10 kilometers. And second, the muon particle itself. So let us assume that the height h above the surface of the Earth where the muon particle is formed to be point A for just referencing, and the photonic detectors on the Earth to be point B. So in the instance when the muon moves from point A to point B, let us assume that for the Earth's person 22 microseconds have been passed. Let us assume. So if you put in this equation 22 microseconds, this is it, 22 microseconds, and this is the speed of muon, which is comparable to the speed of light, then you will get the time elapsed in the frame of reference of muon. This means that depending upon the frame of reference, the time elapsed will be different. So if you actually put those numerical quantities that I just told you, you will get that in the frame of reference of muon, only 1.2 microseconds have been passed, which is obviously less than 2.2 microseconds, which is the average life of muon. So it will definitely be able to reach the surface of the Earth and get detected. So whatever I told you till now that the time is relative gets proved in this experiment. That is, if we change the frame of reference, the time elapsed also changes. Like the person standing on the ground has felt the passing on of time by 22 microseconds, but in the frame of reference of muon, only 1.2 microseconds have been passed. So if you change the frame of reference, the time elapsed will also be changed. Will not only limit our mind towards the experiment we did with muon. We can also have its important practical implications for things like GPS satellites. the GPS satellites rely on extremely precise timings. And hence, to ensure their proper functioning, we must take into consideration the effects of time dilation while making mathematical calculations for them. So, before ending, I would like to ask you one question. Is time travel possible? And most importantly, into the future? According to whatever I told you till now about the fastening of time or slowing down of time, you can think and give me an answer about how will be the pace of time and how can we hop into the future.
Depends on what you take as going to the future. But technically, if you were to travel close to the speed of light for a considerable amount of time, then if you come to like come back to Earth, so if you traveled for 1 year, it might be that on Earth 8 years would have passed, so you would have technically time traveled 7 years ago.
Yeah, but the problem with your solution is that if we travel at the speed of light, our mass would be infinity. So we
I
cannot
said
travel.
close to, I didn't say that.
Then also it will be so high that you will require infinite amount of energy to propel yourself.
It's not infinite, it's relatively.
Huh?
It will be very high. Very high.
So any other? Yeah, it is correct. It is correct. Okay. Yeah.
Are we not traveling in the future right now? 1 second.
Not like that. A considerable amount of gap, I'm saying. The time.
What if you can make a wormhole that connects to a hyperspace that is in the future or the past?
Wormhole helps you to go from one
So what?
point in
You
space
said
to
time
another.
and space are totally relative. So there
Yeah.
can be a space which already has a past of your own.
No, what?
I mean, makes sense. Because
No,
time is...
Not able to be.
There can be a hyperspace which is existing, which is
Yeah,
similar
it can
to...
exist, but I don't know about at the same moment as we are entering the wormhole and we are entering another dimension in which we are experiencing the past. Because according to the theory, space and time are related, and when the concepts of space and time are merged, we get a 4-dimensional coordinates, 3 of which you know, x, y, and z, the coordinates of space, and the 4th coordinate is the coordinate of time, that is time itself. And the physicists today believe that time is linear, that is you can't go back in time. That's why while asking question I was specific that how can you go into the future? Because of linearity of the time, you will not be able to go into the past, and going into the past will create paradoxes. So one of the solution is what he said, and another solution is a direct reference from the movie Interstellar. That is, you can go and live near a black hole where the time has dilated to so much extent that for the 1 year of Earth, it is only 1 second at that planet. So while living on that planet, you will experience only 1 second. But in that 1 second, nearly 1 year has been passed on Earth. So you can travel through a wormhole, but wormhole will take you from one coordinate in space to another. It will not take you from one coordinate in
Okay,
time to
that
another.
could be a possibility that there is a hyperspace which...
What is hyperspace?
I mean, okay, that...
No, it's okay. We can take into consideration that. Okay? No, we are creating a wormhole. I'm saying no. We are going near a black hole through a wormhole.
So technically speaking, by the current technology, it's not possible.
Okay, let me continue. At last, we will take questions. So, on the verge of conclusion, I would like to say that time dilation is a fascinating phenomenon that has various important implications for our understanding of space and time. The study of time dilation also helps us to understand the effects of motion and gravity on the space-time continuum, and hence enables us to have a deeper appreciation for the complexity of the world around us. Let us remember that nature tries to guard her secrets through the unbreakable laws of physics, and hence to decode them, we'll have to strive much harder. Thank you. Any questions now? Okay, I'm open to questions.
So as explained, hypothetical time. What exactly do you mean by hypothetical? And if it is an actual dimension, what are actual tangible dimensions?
Actual tangible directions are 3. Okay, and the hypothetical dimensions are 10. According to strict theory, there are 10 dimensions on which our universe operates. But only 3 can be perceived by us, and 4th also, if you can perceive time. Like when you are sitting in a class, you can feel it is getting slow, it is getting fast. That is also perception of time, but three physical dimensions do exist. That is length, breadth, and depth. That are physically, mathematically you can.
So, you quoted string theory for it, right? So, but there is a concept called circadian rhythm where I'll switch to you frequently like switch between general relativity.
Because time dilation is mentioned in the general relativity. It has been patented to Albert Einstein, no one other. It has been first
Just
mentioned.
listen to me. Frequently switch between special theory and general theory.
Yeah.
Actually, I don't know the difference between the two. Can you elaborate?
Okay, the special theory of relativity always assumes that objects are moving in an inertial frame. That is, they are not accelerated. But you know that whenever we walk, our velocity is not constant. We are constantly walking, we are constantly stopping. So we are ourselves and non-inertial frame of reference. The Earth, the planet, everyone is revolving. They are also non-inertial frame of reference. The special theory always is applicable on inertial frames. So it is not applicable in the real world, because in real world everything is non-inertial. Most of all the things are non-inertial. That is why Albert Einstein had to spend next 10 years in finding the laws of physics for non-inertial frame. And what is applicable on the non-inertial frames is quoted in the general theory of relativity, published 10 years later, or special theory of relativity. Okay. Anyone wants to ask me? Yeah.
By the current technology,
I didn't say current. I'm not saying current we are not able to do
by
anything.
current we can't do remote to close to speed of light.
For reaching moon itself